Hi, Honors Algebra 2. This is Miss Kraft. We are going to be doing lesson 14, which is complex numbers, um, which really means we're talking about this letter I in math. So we're going to be defining and using the imaginary unit I and perform operations including add, subtract, and multiply complex numbers. We'll also be finding solutions. So first of all, a little bit about the imaginary number. If you want to pause me and read through that, you can, but for time's sake, I'm just going to tell you his name is Euler, not Euler. That's always up for discussion. He invented an imaginary number so that math could continue on. So before, when we got to, I know you guys have been told this before, like you can't take the square root of a negative because a negative times a negative is a positive, and a positive times a negative, that wouldn't be a square root because we have to have two of the same thing that multiply together to get to what's under the radical. So he advanced that for people, and so we actually use these things in electrical circuits and other things in life. So this is a good thing to read about if you're interested in, and we'll be going into the algebraic piece of it now. So this is where complex numbers lie. We are going to talk a little bit about what I is. So when we talk about I is the square root of -1. So all of our imaginary numbers are actually going to be rooted from this, and we can relate back to the square root of -1 being I. When we move on to I squared, we see that it's the square root of -1 times the square root of -1, which we know when we multiply square roots together, we just are left with what's underneath the radical, and so it's actually just -1. So I squared is always -1. I to the third is going to be this -1, right, which was to the second, plus another one, right? We got to multiply it by another one, which will be another -1. But we're just going to call that -I because we have -1 and then this guy is I. So we'll call it -I. There. I to the fourth. I to the fourth is our I squared 2 times, right? I squared times I squared. And I squared is nice because it's -1 times -1, which is 1. So this is a good thing to remember. We'll talk about it in the next lesson as well. But basically, we want to always remember, whoops, my highlighter's off there, that I is -1, I squared, I is I squared is -1, I to the third is -I, and I to the fourth is 1. So if you need to, go ahead and pause because we see this cycle happen over and over again. So I to the fifth then becomes back up to just I, and I to the sixth becomes -1, and I to the seventh becomes -I, and I to the eighth is again 1. So any multiple of 4 for your exponent ends up being 1. So these 4 are the ones you're going to want to memorize. All right, simplifying radicals using imaginary numbers. So the square root of -1 we know is just I. When we get here, we can pull that -1 out. Basically what happens is we have the square root of -1 times the square root of 4. So the square root of -1, that's just our I, and then the square root of 4 is 2. So we write this as 2I. Imaginary numbers are second, almost like a variable. For this one, same thing. So we have I for sure, and then the square root of 9 is 3. Okay. 25, the square root of 25 is 5, and we know I is the square root of -1. 36, same thing. We have 6I. Now over here is where it gets a little more tricky. So I don't know if you guys remember in honors geometry or in algebra 1 when you learned how to simplify a radical, but basically if we didn't have the I, okay, if we just had a positive square root of 18, we would find a perfect square that fits into 18. So a perfect square that fits into 18 would be 9. So we want to multiply 9 times 2. And that's the same thing as separating them apart as the square root of 9 times the square root of 2. Right? And now we know the square root of 9, that can turn into a much nicer number, and we call that 3. and then we still have the square root of 2, which we can't take. Okay, so that is just how positive 18 works. And it works the same way with a negative. We just have I in there. So we're actually going to have 3I square roots of 2. And those aren't actually equal, right? But with the negative, this would be our answer. Okay, so then we'll have to use the same method down here. So the square root of 75, of negative 75, we know we're going to have an I in the end. And so we can just pull an I out if you want to. And then we'll have a perfect square, which would be 25 times 3. And we can then change that to 5I square roots of 3. Same thing down here. Again, if you want to, go ahead and pause me and then see if you get the answers right and fast forward. 200, it would be 10. So we know that it is 100. So I times the square root of 100 times 3. Well, we know the square root of 100 is 10, so we can simplify that out. So I have 10I square roots of 3. Same thing here. 51 actually does not have any factors, so we're just going to call it I square root of 51. And then we have 144. So 144 has a perfect square of 12. Now this negative is not under the radical. So actually it's almost like having this in parentheses, and we do that first and then we apply the negative. This answer is negative 12. It is not divisible it is negative 12, and it is not an imaginary number. That would be imaginary if it was a negative inside there. Okay, moving on. So another thing I want to point out actually before I move on is that we are not solving, we're just evaluating. In these cases, we're evaluating. It's asking us, what is this? So there's just one answer. When we talk about variables, like we will on the next slides, we will actually be solving, and we'll have to consider a positive or negative answer. So for instance, x equals the square root of 25. Right? X actually could be 5, and X actually could be negative 5. So we have to consider our plus or minus option in this case because we were solving for X. If it just tells us the square root of 25 equals, well, there is no option there, right, for solving. It's just 5. Okay? All right, moving on. Find the values of x and y that satisfy the equation. So I'm going to do this one, and then you guys will pause me and do the second one. We're going to set real numbers, right? We can solve for a real number with x, and this is a real number. So a complex number in itself is just having a real number plus, and then the imaginary number is always second. So this is a real, and this is an imaginary and an imaginary. So a real and an imaginary make up a complex number, right? So we'll set the reals equal to the reals and the imaginaries equal to the imaginaries. So we'll have 2x equals 10. And then for our imaginaries, we'll have negative 7i, don't forget the negative, equals yi. Well, what is x? That's pretty simple. It's 5. Now, we have to solve for y in this, right? Because imaginary numbers are numbers. We don't want to solve for, we don't want to solve for I. We just want to solve for y. So we're going to divide by I to get y by itself and divide by I over here. And what ends up happening is you get y equals negative 7. So even though they were imaginary to begin with, when we have complex numbers that have reals and imaginary, it's possible to come out with 2 real numbers, which is why Euler was so famous. Okay, go ahead and pause me, and then I'll show you the answers for the next ones. All right, so here we are with our answers for the last two. We have our real number with x equals to 9, and then y equals negative 3. And then over here we have negative 9/2 for x, and we have 3/4 for y. Pause me if you need to go ahead and look at that work. All right, Add or subtract. Write the answer in standard form. So this is a complex number form. So we want the imaginaries last with our coefficients in front of them. So when we add these, we can either set them up like a big addition problem, or we can just, whoops, combine them, right? So 8 plus 5 is 13. Negative I plus 4i is positive 3i, and that's in the correct form there. Okay, it gets tricky with a subtraction problem. So a subtraction problem, you're actually going to have to line it up like this and write a big subtraction sign out here, or you're going to have to distribute the negative before you do that. So I will show you what I mean by distributing the negative. So get rid of the parentheses first, right? So 7 minus 6i minus 3, and then minus a negative 6i is going to be plus 6i. And now you can just combine like terms. So you'll have negative 6i plus 6i actually go away, and 7 minus 3 is 4. Okay, so just a couple different strategies. For this one, I would just go ahead and distribute that negative. 13 minus 2 minus 7i. Now my parentheses and my negative is distributed, and the signs actually go with the number ahead of them. So 13 minus 2 is 11, and negative 7 plus 5 is negative 2i. Okay? Go ahead and pause me and do these questions, and then I will resume and show you the answers. And then the rest of this lesson will actually be on another video. All right, here are the answers for the last 4 example problems. And then go ahead and start the next video, which is going to be more of our solving and finding solutions.